Now let's talk about finding the pH of a 0.1 molar NaF solution. So NaF is also a soluble salt, right? We know it's a salt because it contains a metal, Na+, and a nonmetal ion, F-. So we're going to dissociate it completely into its Na+ and F- ions. We'll write that reaction out. And again, the dissociation is complete. It goes 100% of the way to completion. And so we use the one-way arrow there. Now, I want you to list out the major species that are going to be present in this solution and predict whether this solution is acidic or basic or neutral. So take a moment to work through this, and if necessary, take a look at the table of acids and bases to help you answer this question. And on the other side of the question, we'll go over the answer together. All right, let's go over the answer. So what we're going to do is list out the major species that we have here. We have Na+, we have F-, and we always have water. Na+ is a metal cation, and in a previous video, we talked about how metal cations will have no acid-base properties, and they will just behave as spectators. For the F-, when you take a look at the table of acids and bases, you see F- here in the column of bases, right? And it is a weak base. So F- is a weak base. And water is a very weak acid or base. Therefore, this solution contains water and a weak base. Therefore, this solution must be basic. The answer here is B. Now let's talk about how we would calculate the pH of this solution. So the idea behind this is to use the list of major species to help us write the reaction that governs what the pH is. We'll go back and take a look at the list again. And what we have here is our weak base, F-, reacting with water, right? Na+ is just a spectator. So since F- is a base, water will have to act as an acid in this reaction. Because both are weak, this will be an equilibrium reaction. All right, so what we'll get for our reaction is F- reacts with water. And again, both are weak, so it's equilibrium. Because F- is a base, it is a proton acceptor. It will gain an H+ to become HF. And because water is acting as an acid in this reaction, it donates or it loses a proton to become the hydroxide ion. Now, it's important to think about what type of a K we're dealing with in this problem. And because we produce the hydroxide ion, we're going to be dealing with a Kb here. Now, we could write the Kb expression, that is concentration of HF times the concentration of hydroxide ion over the concentration of F-. And in writing that out, we'll see that our goal in this problem is going to be, in part, to find what this concentration of hydroxide ion is at equilibrium, because that will dictate the pOH of the solution, and then that will tell us what the pH of the solution is. Incidentally, at the outset, before we really go deep into doing calculations here, it's beneficial for us to make our prediction of what a reasonable answer would be. And because we predicted that the solution was basic, we predict that a reasonable answer for the pH has to be a number greater than 7. So if at some point you get a pH that's less than 7 in this problem, it tells you that you either made a mistake or maybe there are some more steps that you need to do in solving the problem. To go further in this problem, we'll also need to know not only the Kb expression, but also the value of Kb. And to find the value of Kb for the fluoride ion, we would have to use our relationship between Ka and Kb. Right? Kb can be found by doing Kw, that's 10 to the minus 14, over the Ka of the conjugate acid, HF. Kb is 10 to the minus 14 over the Ka of HF is 7.2 times 10 to the minus 4. And so the Kb for the fluoride ion is a really small number. It is 1.4 times 10 to the minus 11. Right, so the small x approximation will really come into play here. We'll now make the ice table so that we can relate the initial amounts to the equilibrium amounts that we're looking for in order to get the answer to the problem. The solution was 0.1 molar NaF, and again, it dissociates completely into Na+ and F- ion, right? So, and it's at a 1-to-1 ratio, so you're going to have a 0.1 molar concentration of the fluoride ion. We don't care about how much water is there because it's not part of the Kb expression, so goodbye to you. And for F minus, initially there will be none, and initially no hydroxide ion. This reaction will proceed to the right, so we'll fill in the rest of this ice table on the change line and put it all together to get the equilibrium line. Again, because the value of Kb is so small, you can take the small x approximation and approximate the equilibrium concentration of the fluoride ion to be 0.1. You can now plug everything into the Kb expression, and when you do that, you're going to have 1.4 times 10 to the minus 11 equals x times x over 0.1. You can now solve this equation for x, and what you end up getting is that the value of x comes out to 1.2 times 10 to the minus 6. Now, I've mentioned before the importance of thinking about the relevance of the value of x, and that becomes particularly important in this problem because it will help you to keep focused on what you are finding and what steps you need to do next. So whenever you get the value of x, you have to go back up to the ice table and look at what x represents. X represents the concentration of hydroxide ion. So what we can say is that the concentration of hydroxide ion is 1.2 times 10 to the minus 6. Since we have the concentration of hydroxide, we're going to use that to find the pOH of the solution. So the pOH is the negative log of the hydroxide ion concentration. The negative log of 1.2 times 10 to the minus 6 is 5.9. And it might be very tempting at this point in the problem to think that you might be finished because you've taken a negative log and you have some number, maybe you think you're done. But it's important, as always, to make sure that you're labeling all of the variables as you're going through all of this and to recognize that this is pOH. And additionally, keep in mind that our final answer has to be a number greater than 7. So we're not done yet. We still have one more step that's left to do, and that's to convert the pOH into a pH. So that's done with our pH plus pOH equals 14 equation. And so the pH will be found by subtracting the pOH from 14. The pH of this solution is 14 minus 5.9. That is 8.1. This is a number that makes sense, right? This is a pH that's above 7. This is a pH that indicates a basic solution. That brings us to the end of this example in this video. Next, we'll talk about a 0.1 molar NH4F solution